In this video, we'll continue our discussion of symmetry with the parity operator. We'll first introduce the operator, talk about parity in 3 and 1 dimensions, and then generate selection rules based on the parity operator. So, let's consider a wave function, psi, and apply the parity operator pi, which reflects the function about the origin in 1 dimension. So a function that had this peak at x now becomes a function that has a peak at minus x, and everything else is inverted. Mathematically, this is described in 1 dimension as pi applied to psi of x is equal to psi prime of x, which is equal to psi of minus x. In 3 dimensions, you have pi applied to psi of x, y, z gives you psi of minus x minus y minus z. In crystallography, this operation is called inversion. And inversion in 3 dimensions is equivalent to a mirror reflection through a plane, say this plane in the xz plane. So you reflect, and then you rotate 180 degrees about a perpendicular axis. And now you have a completely inverted system. So in 1 dimension, pi inverts space. That is, pi applied to psi of x is equal to psi prime of x is equal to psi of minus x. This operator is its own inverse. It's Hermitian, and therefore it's unitary. So that means that pi, the inverse of pi, is equal to pi, but it's also the Hermitian conjugate of pi. Remember that operators transform under spatial inversion in the following way. We take an operator Q, we sandwich it between the Hermitian conjugate and the operator itself for the transformation, and you get Q prime. Specifically, the position and momentum operators are odd under parity. That is, if I take X operator and apply a parity operation, that means that I apply pi dagger to X, it walks through, and then these two are inverses of each other, so that gives us 0, or 1 rather, and that means that all you've done is invert the x coordinate. So x prime is equal to minus x, that operator. And the same thing with the momentum, p prime, because it's just a single derivative, it's pi daggers applied to p gives you minus p, and then the pi dagger and pi give you 1 because it's unitary. So any operator q, because they're all made up of x's and p's, must transform like this. So q prime of x and p is just q of minus x and minus p. So a system is said to have inversion symmetry if the Hamiltonian is unchanged by a parity transformation. That is, if h prime is equal to h, where you've now done a parity transformation on the Hamiltonian itself. Well, if we take that expression, h is equal to h pi dagger h pi, right? That's what we're saying by its invariant. And then we put a pi, another operator pi, we apply that to the either side. Then what this means is that this becomes the identity matrix, and you have that pi applied to h is equal to h applied to pi. And so this means that the commutator of h and pi is 0. So the parity operator commutes with the Hamiltonian because when you apply the parity operator, the Hamiltonian is unchanged. So for a Hamiltonian which describes a particle of mass m in a one-dimensional potential, inversion symmetry means that v of x is it's equivalent to v of minus x. That is, v of x has to be an even function of position if you want the Hamiltonian to commute with the parity operator. Because pi and h commute, we can find common eigenfunctions of both, such that psi sub n of x is given by the following. That is, when we apply the parity operator to psi sub n of x, and it's a common eigenfunction of the Hamiltonian and the parity operator, then you're supposed to get psi sub n of minus x, but that should be either plus or minus psi sub n of x. That's because the eigenvalues of parity can only be plus or minus 1. It's the only option you have if you want to make this be an eigenfunction of the parity operator as well as an eigenfunction of the Hamiltonian. So the eigenfunctions of this Hamiltonian are either even, that's the plus sign, or odd under parity. And because of Ehrenfest's theorem, we've seen that before, d by dt of the expectation value of the parity operator is equal to I over h bar times the expectation value of the Hamiltonian and the parity operator, and this must be equal to 0. Parity operator clearly has no time dependence. But this quantity is 0, and so the time dependence of the expectation value of the parity operator is also 0, time derivative. This means that parity is conserved in time. So an even function that starts as an even function under parity will remain an even function for all time, and similarly a function that's odd under parity will remain odd for all time. So in 3 dimensions, things are a little bit more complicated. The parity operator inverts the system through the origin, right? So if you have pi applied to psi of r, then psi, that equals psi prime of r, but psi prime of r is just psi of minus r. So the r and p operators, and any arbitrary operator composed of r and p, must transform just like the r and p operators do here. That is, r prime, which is transformed by pi dagger r pi, is equal to minus r, and p prime in 3 dimensions, now these are in 3 dimensions, is pi dagger p pi is equal to minus p. That means that q prime, as before, in 1 dimension, is just now, when you transform it, you get q of minus r and minus p is equal to q prime of r and p. So the Hamiltonian in 3 dimensions will have parity and will be commuting with parity when v of minus r is equal to v of r. Now, if you have a central potential, like many potentials in physics, this is absolutely true. So the eigenstates of the hydrogen atom are also eigenstates of parity because the hydrogen atom has a central potential which is even under parity inversion. That means that if we apply parity operator to psi of NLM of r, theta, and phi, it's got to be equal to minus 1 to the nth power, turns out it's minus 1 to the nth power, psi NLM of r, theta, and phi. Where psi of NLM sub NLM of r, theta, and phi is just the radial function r sub NL of r, and the spherical harmonic YLM of theta and phi. The selection rules, which are going to be important when we talk about time-dependent phenomena later on in the book, indicate when a matrix element couples 2 states. So if you have a state A and B, you put an operator, you take the expectation value of the inner product with the operator in between. This parity, the selection rules from parity are very important in telling you whether this matrix element will be 0 or not, based on symmetry. So one of the more important operators that we'll use is the electric dipole operator, which we designate as P sub E, just to take it, make it indistinguishable from the momentum operator. And that's just the charge times R. So that's a dipole, right? It has a direction and a charge. So the selection rules for this electric dipole operator will determine which atomic transitions are allowed and which are forbidden. So this operator, the dipole operator, P sub E, must be odd under parity because R is odd and Q is just a scalar. So pi dagger, P sub E, pi is equal to minus P sub E operator. Now let's consider the matrix elements for an electric dipole operator between two atomic states. One state has quantum numbers n, l, m. The other one has quantum numbers n prime, l prime, m prime. So what we're doing is we're taking the matrix element, which means we put n prime, l prime, m prime on one side, P sub E in the middle, and n, l, m on the other side. Well, we know that if we transform this operator P sub E by putting pi dagger in pi, you get minus P sub E. And so I know that this is going to be equal to the negative of the of the matrix element of n prime, l prime, m prime, and NLM of pi dagger P sub E pi, because these two are equal. But we know what the pi dagger operator does, because we can move it over here and it becomes a pi, and when you apply it to this psi of NLM, we get minus 1 to the L prime power. When we take this parity operator and apply it to the right, to the ket, we get minus 1 to the L power. So we're left then with an inner product, or a matrix element of n prime, l prime, m prime of P sub E with NLM, which is exactly what I had on the left side. But now we've built up this additional factor, which is a minus 1 to the L plus L prime plus 1. Because you had that extra minus 1 at the beginning. And that's equal to 0 if L plus L prime is equal to 2n. Because if L plus L prime is equal to 2n, then you get a minus sign out of here. And you can't have these two matrix elements be the negative of each other. So this only works if L plus L prime plus 1 is equal to an even power, or an even value of n. If the whole quantity is equal to even value of n, then this becomes 1, and you can have an equality. So this is a selection rule. L plus L prime is equal to 2n means you get a 0 in the matrix element.